Good evening. So, please tell your friends to join the class. So, if anybody there, please tell to join the class. If anybody there, please say hi, hello, or good evening, etc. Please write in the comment section. So, today I am going to discuss random effect model, one-way Anova random effect model. So, before starting, please tell your friend to join the class. And okay, who are you? Please say hi, hello, or etc. in the comment section. So, can I start? Please tell me. Can I start? Please tell me. Random effect model. Before discussing random effect model, I define balance. The definition of balance is definition a one-way and higher order classification is called balance if the number of observations in the group or in cell are called a one-way classification is called balance if the number of observations in the group or in cell are equal That is, as smaller the variance, the better the estimate. We already observed that the variance of the estimate is minimum when all the observations of the cells are all equal. So a one-way classification is called balance if the number of observations in the groups are equal. The one-way ANOVA is most efficient if Ni is a number of observation in the ith cell is equal to N naught for all I. That is, if the classification is balanced. Now we consider random effect model, one-way ANOVA random effect model. Suppose that as a measure of quality control, and auto manufacturing auto manufacturer test a sample of mucor observing for each car the mileage achieved on a number of occasion on a liter of petrol. So here I consider example. Suppose that as a measure of quality control, an automobile manufacturer tests a sample of new car, because it is not possible to test all the cars. So we always select a sample of cars and then observing for each car the mileage achieved on a number of occasions on liter of petrol. So this is the case of random effect model instead of uh, fixed effect model, because here we consider a sample of car rather than all cars. Okay, so in that situation we use random effect model instead of fixed effect model. So we define, suppose Yij is, is the mileage of ith car on the jth occasion. Let mi be the true mean for the ith selected ith car selected. So one thing I mentioned that before writing this sentence. So this is the difference between fixed effect model and random effect model. In fixed effect model, we uh, consider all the treatments. Here I discussing the context of one or Anova. When we consider all the treatment, this is a fixed effect model, but it is not always possible to consider all the treatments. This is the case where we do not consider all the cars because it is really impractical. It is not possible to collect all the car and then uh, check this liter of petrol mileage achieve on check the mileage uh, achieved on number of occasional liter of petrol. So in that situation we do not use fixed effect model. In this situation we use random effect model because it's not possible to select all the cars. So hence we consider a sample of cars in that situation. Okay, so this is the difference between random effect model and fixed effect model. The first difference we will discuss later. There are other points. So now we define mi with the true mean for ith car selected. Then we may write Yij equal to mi plus Eij, where Eij is the error of the ith car on the jth occasion. So where Eij is the error of the ith car on jth occasion, however The manufacturer is interested in the performance of the thousand of cars to be produced that year, and for this reason has drawn a random sample of cars for test. Hence, MI, MIs, because we selected a random sample of cars, therefore MIs are the effect effects of the cars selected randomly from the large population of cars, and the cars selected can be any cars from the population of cars. Consequently, MIs are random. Let mu be the fixed general effect and we define the effect of the ith car in the experiment is AI equal to MI minus mu. Then the model 1 becomes Yij instead of mi, we write mu plus ai plus ei, where the effect ai of the ith card is a random variable. Without loss of generality, we assume expectation ai equal to 0 and variance of ai equal to sigma x square. So why I assuming expectation ai equal to 0? Because expectation of yij equal to mu, hence expectation ai equal to 0. Okay. Therefore, the model is yij mu plus ai plus eij, where ai and eij are completely independent and ai follow normal 0 sigma square. I assume that ai follow normal 0 sigma square independently and eij follow normal 0 sigma e square independently for all I and j. The variance of observation yij, that is variance of yij equal to variance of ai plus variance of eij. So sigma is square equal plus sigma is square. And so it is. So this implies sigma is square, I think it is capital and not small a. So sigma a square and sigma c square are called components of the variance of an observation. The intra class correlation coefficient rho is the ordinary correlation between any two of the observation Yij and Yij dash, where j not equal to j dash. Because I use the term intra. Intra means within a group. So I consider only the correlation between Yij and Yij dash, where the that is we consider two observation from ith group. Okay, so this is the simple correlation between these two observation in the same level or same group. Here I label consider as a car, so I write it here or car. So same label I or car I. Okay, so the correlation is, I denote this by rho star, which is covariance between Yij Yij dash divided by variance of Yij, variance of Yij dash, which is equal to Yij minus mu Yij dash minus mu by, because this variance of Yij, variance of Yij dash is nothing but a sigma a square plus sigma e square. So I write it, or simply you can write sigma y square, because variance of Yij is constant. So, and this is equal to sigma a square. You can check this thing, just check it, and it is equal to, that means sigma a square is nothing but a, actually you check that sigma square is nothing but a Yij, covariance between Yij dash is equal to sigma a square. So please check, this is your homework. So this is equal to sigma a square by sigma y square, and where sigma y square is nothing but a sigma a square plus sigma e square. So rho star equal to sigma a square by sigma a square plus sigma e square. Therefore Yij is not independent, but you should note this point. When you consider fixed effect model, then your Yij are independent, but here for random effect model, Yij's are not independent. Is a dependent variable, are dependent, and the joint distribution hence the estimation of and their joint distribution. Therefore, Y's are dependent, and they have a joint distribution. You write they have joint distribution. Hence, the estimation of sigma e square and sigma e square is greatly simplify if the model is assumed to be balanced. That is, to satisfy n equal to r for all I from 1 to k. Therefore, we summarize the assumptions made for Yij. This is the model mu plus ai plus Yij, and here we use k plus rk random variable, k because I run from 1 to k. So for AIs we have a k random variable, and for Aij there are r into k. So in total k plus rk random variables. AI and Aij are completely independent. The AI and Aij completely independent. AI follow normal 0 sigma is square, and Aij follow normal 0 sigma is square. Okay. Therefore, the total number of observations here it is r into k. Our hypothesis is the hypothesis usually so can you give me 5 minutes? There is a technical problem. I'll be back within a 5 minutes. Please give me a 5 minutes. The hypothesis, okay. The hypothesis usually tested usually tested in the present model for one-way Anova or one-way layout is h naught colon sigma a square equal to 0. Here, for fixed effect model, we test all tau i's equal to 0, but here we test sigma a square equal to 0, and we see that if sigma a square equal to 0, that means your intra-correlation coefficient between yij and yij dash equal to 0. So this, because null hypothesis means there is all the effects are equal, so this means your correlation coefficient, intra-class correlation coefficient should be 0, and rho star should be 0 implies sigma a square equal to 0. So we said this hypothesis h naught colon sigma a square equal to 0. Obviously, corresponding alternative hypothesis h1 sigma a square not equal to 0. Okay. And this test means that is the test whether all the labels in the population have the same true mean. Analysis. Here we notice that the least square method and testing of linear hypothesis etc. are not applied here, but we can use this result here. Actually, I mean to say, you note that this thing, the least square method and testing of linear hypothesis etc. applied only when we consider fixed effect model, but for random effect model, since AIs are random, so there is a therefore AI is not a parameter, so we cannot apply least square technique here. So therefore the SS occurring in the fixed effect model will not occur in the random effect model in the same way. So you should keep this point. Since AI is random here, it is not a fixed effect, so we cannot apply this square technique. So we cannot use the therefore SS occurring in fixed effect model will not occur in the random effect model in the same way. Okay, you should keep this point. You should remember this point. Okay, so I write this thing before starting this analysis portion. You should write this thing: the least square method and testing of linear hypothesis etc. are applied for linear model, which are linear model means which are linear in parameters, which are linear in parameters. In random effect model, Yij equal to mu plus Ai plus Eij is not a linear model as alpha is are random. Instead of alpha is because here I write alpha is because you can easily correlate it with the case of fixed effect model. So in fixed effect model we consider alpha is are fixed, but here alpha is are random. So alpha is means I denote this alpha is by Ai are random, not parameter. Okay. Therefore, the S's occurring in the fixed model, fixed effect model, will not occur in the random effect model. In the same way, the general procedure used to obtain not obtain, used to obtain taste and estimates with random effects models and mixed model in balance cases. And in mixed model in balance cases is to consider all mean square in the usual Anova table with corresponding fixed effects model. Fixed effect model is the model for the population of all label but random effects model for the population of is the model random effect model is the model for random sample for a random sample of labels from the population of all labels. We know this. So we expect that the SS sum of squares of all labels are also valid for the number of also valid for the random effects model, since model we expect that the sum of square for all labels are also valid for random effect model. Arising of labels arising from a random sample of labels. Okay. So that means I want to say, so we use all SSS fixed effect model here also. So the SS occurring, therefore we write the SS occurring in the Anova for one-way fixed effect model are SS due to H naught, which is we write SSA. We know this thing. Since here I use balance case, so all NIs are equal to R. So instead of NI, I write R here yi naught bar, y naught not bar whole square, and SSE sum of square due to error. We recall all the result of fixed effect model here also. Result means SS. Okay. So I consider all the SS of fixed effect model, that is SS due to factor A and SS due to error. So you know this is the ith group mean and this is a grand mean and yijth observations, ijth observations. Under the random effect, model, yi naught bar equal to mu plus ai plus ei naught bar, y naught not bar equal to mu plus a naught e naught not bar. So therefore this implies SSA is R e to I from 1 to k, this is k, this is k, I from 1 to k, yi naught bar minus y naught not bar whole square is equal to R into I from 1 to k. Yi naught bar means mu plus ai plus ei naught bar minus mu minus a naught minus e naught not bar, which I write ai plus ei naught bar minus a minus e naught not bar whole square, and similarly SSE is equal to I from 1 to k, j from 1 to r, eij minus ei naught bar whole square. Okay. Now let gi, which is equal to ai plus ei naught bar, and then this gi follow IID normal 0, because expectation of gi is nothing but a linear combination of normal parameters. So this normal variables, this means from the results of normal distributions, gi also follows normal distribution with mean of expectation of gi. So expectation of gi is 0 because the expectation of ei and expectation of eij all are 0. So this implies expectation of gi equal to 0 and variance of gi is nothing but a variance of ai plus ei naught bar, which is sigma square. We check this, sigma square by r. Okay, so we consider this value by sigma g square. Okay, therefore we write to gi follow iid normal 0 sigma g square, where sigma g square is equal to sigma a square plus sigma a square by r. So erase this line, just write it. Okay, so from the using the sampling distribution of sample variance, because it look like a, if you look at this expression of SSA, this is nothing but a r into I from 1 to k gi minus g bar whole square. Okay, so if you use the sampling distribution of sample variance, we know the result. I just state the result. You know this thing. If that is, if x1, x2, xn follow independently normal mu sigma square, x1, x2, xn follows independently normal mu sigma square, then x bar sample mean and s squares sample variance are independent, and n minus 1 s square by sigma square follow chi square with n minus 1 degrees of freedom, and x bar follow normal distributions. Okay, so I use this result. So therefore I from 1 to k gi minus g bar whole square, and the variance is sigma g square. This is follow chi square with k minus 1 degrees of freedom, and since then this result imply SSA follow R into, because if you look at the expression of SSA, then this follows, SSA follows R into sigma g square chi square with k minus 1 degrees of freedom. Okay. So this result imply expectation of SSA, which is equal to R sigma g square into k minus 1. So this means expectation of SSA by k minus 1, with which we know MSA mean sum of square due to error, is equal to R sigma g square means sigma a square plus sigma e square by R. So therefore expectation of MSA is equal to R sigma a square plus sigma e square. Okay. Now consider the expression of SSE, then we can we can show that SSE follow sigma e square chi square n minus k, where n equal to rk. Just see the expression of SSE. Look at this expression. So from this expression we can write this thing. Just use this, you know, sum over j from 1 to ni. Just use this, the sampling distribution of sample variance. It look like that. Follow chi square with ni minus 1, and since this is independent for I, that means if you write this as a wi variable, then w1, w2, wk are independent. So using the additivity property of chi square distributions, we write this is follow chi square sum over ni. Here ni means, sorry, this is k. Okay, j from 1 to k. So it should be chi square k minus 1, because I consider balance case. So using the additivity property of chi square distribution, this is follow chi square with n into k minus 1. Sorry, I think it is the r, not k. Okay, is changed. K is the number of factor, R is the number of observations in each cell. Okay, so it should be R, not K. So this is R minus 1. So I from 1 to K. So this follows chi square with K into R minus 1, that is KR means n minus. Okay, so just using this fact, we can write SSC follow sigma square n minus K. I forgot to add this, multiply this multiplier. This is sigma square into chi square R minus 1, sigma square into chi square K minus R minus 1. Okay, so SSC follow this. So this imply expectation of SSC is sigma square n minus K. This imply expectation of MSC, mean sum of square due to error, which is nothing but SSC by degrees of error, degrees of freedom. So this is equal to sigma square. Here also MSC is unbiased estimator of sigma square. So therefore expectation of MSA, which is R into sigma square. So we write sigma square means MSE plus R into sigma square. So this means MSA equal to MSE if H naught sigma square equal to 0 holds. Otherwise, it is strictly greater than expectation of MSE. H naught is false. Okay. So we have MSA by MSC approximately 1 under H naught, and MSA by MSC, I talking about observed, okay, should be greater than 1 when H naught is false. Hence, MSC is a valid error for testing H naught and hence the test statistics is F ratio, which is MSA by MSC. Because MSC is a valid error, so we can use this. And since MSA and MSC are independent, please check in your homework. MSA and MSC are independent. please prove this in the context of random effect model. So since these two are independent and these are follows chi-square distributions, so the F ratio MSA by MSE follow F distribution with k minus 1 n minus k degrees of freedom under H. So we reject H naught at level alpha if F MSA by MSC greater than F alpha k minus 1 n minus k. I already defined F alpha k minus 1 n minus k is the upper alpha percentile point of F distribution with k minus 1 n minus k degrees of freedom. Okay. So remark one, since F which is MSA by MSE, this is follow R sigma square plus sigma square chi square k minus 1 k minus 1. This is for MSA divided by sigma square chi square n minus k by n minus k equal to 1 plus r theta chi square k minus 1 k minus 1 divided by k minus 1 its degrees of freedom chi square n minus k n minus k. So here r sigma square equal to sigma square, we write this 1 plus r theta where r equal to theta equal to sigma square by sigma square. So this ratio is nothing but a F distributions with k minus 1 n minus k degrees of freedom. So in general, when H naught is not true, this ratio follows F distribution with certain multiplier, that is 1 plus r theta. This is a central F distribution. So there is another difference. So for fixed effect model, this is a non-central F distribution, but fixed a random effect model, this is follow constant into central distributions under alternative. Okay. So therefore the expected value, this implies the expectation of F is nothing but a 1 plus r theta equal into expectation F k minus 1 n minus k. Okay. So 1 plus r theta is nothing but a 1 plus r theta means sigma square by sigma square, and the expectation of F distribution whose degrees of freedom k minus 1 n minus k is nothing but a n minus k by n minus k minus 2. So both the value this is also greater than 1 because 1 plus something, and this is also greater than 1 because n minus k greater than n minus k minus 2. So product of these two quantities should be greater than 1. So here we observe that even if under H naught, this ratio, this expected value should be greater than 1. But for when obviously when k, this k should be no for all k. Okay, so even if under H naught, this is also greater than 1, but fixed effect model, it is exactly 1. Okay, so for random effect model, in one-way classification data, one-way classifier, I think it's better to write classifier data, the expected value of F statistics cannot be less than unity. But it is quite possible that, and observe, this is based on sample, this ratio computed based on the sample value. The observed F is less than 1. If less than 1, then MSA less than MSC. Here MSC is random variability which we have to allow in the experiment if MSA greater than MSC, then the variability due to A is not random and it has some effect. Here one point you should write, since MSA less than MSC, this means since MSC is a random variability which we have allowed to allow in the experiment, so this means MSA effect due to A is insignificant. So we have seen that expectation MSA equal to sigma E square R into sigma A square, and expectation of MSE, which is sigma E square. So this implies expectation MSA minus MSE by R is sigma E square. So hence sigma E square equal to MSE and sigma A square hat is equal to MSA minus MSE by R. You should note this point. MSA, when we in general, MSA is not always greater than MSE, but sigma A square always greater than 0. So when you find the situation, even, or I mean to say, on the basis of observation, your calculation shows that MSA minus MSE less than 0. So in that case, you use unbiased estimator of sigma square equal to 0. Otherwise, you use sigma square hat is equal to MSA by MSE by R. So this is the estimate. So you replace this estimate 0, replace the estimate of sigma square by 0 when MSA less than MSE. Otherwise, this value gives estimate of sigma square. Okay, so we can easily check that these are the unbiased estimator of sigma square and sigma square. Okay, check. So this is an Anova table. Or one-way random effects model. The first column is source of variation. The first component of the first column is factor A. Second component's error, and then total. SSA, just write this thing. When you compute it, just put the value of SSA here. SSE SST and then degrees of freedom. This is k minus 1 n minus k n minus 1 ms, mean sum of square. So MSA is nothing but SSA by k minus 1, MSC SSC by n minus k, expectation of MS, this is sigma square plus R into sigma square, F ratio, MSA by MSC, tabulated F. This is a critical value. level alpha. So we reject H naught when a greater than this critical value, otherwise accept. Okay. So now the next point is distinguish between, I already mentioned some point, between fixed effect model and random effect model. So this is the homework. Please collect all the points, read carefully these two models, fixed effect model, random effect model. In the context of one-way Anova, or you should only consider one-way Anova. You restrict one-way Anova, and then write distinguish between fixed effect model and random. Okay, so this is your homework. You should submit it before coming Monday. Okay, so I want to stop today class here. So if you have any queries, any questions, please tell me. Otherwise, I end the stream, and we will meet again on Monday, same time, 6 p.m. and we will discuss two-way Anova. We start two-way Anova. So that class we will discuss two-way Anova, fixed effect model. If time permits, then we will discuss random effect, mixed effect, etc. Okay. So now, please tell me, have you any problem? Have you any doubt? Please tell me. I will be there. Otherwise, if you have no problem, please mention in the comment section. Then I end the stream. Thank you for watching this video. Thank you all for watching this video. So please mention in the comment section, is there any doubt? Even if you have no doubt, you also mention no problem, no doubt, etc. in the comment section. And then I end this stream. So please take your time and tell me. Hello, are you hear me? Are you hear me? If yes, please write. Please write in the comment section. Have you any doubt in the write in the comment section? If not, even then you write in the comment section, no doubt, no problem, etc. Because I end this stream now. Okay. So I think you have no doubt. So thank you for watching this video. So thank you all. Okay, Sudipta, thank you. Shamurjit is also here. Okay, sir, no problem. Thank you, Shamurjit. Thank you. Okay. Shamurjit, I think you are okay. Okay, no. Shamurjit, Shomojit. It's not Shamurjit. Okay. So Shomojit, Sudipta, thank you. So